Today we're going to talk about non-renewable energy resources. Now, up to this point, we have spoke about energy stores, kinetic energy, gravitational potential energy. And these are things right now that might have energy manifest in that particular store. But when I talk about a resource, I talk about something that might innately at some point have had energy stored within it. Energy that I could unlock now in the present time, that would be useful for our technology. Of course, I'm talking about those fuels or resources that can produce energy that would be unlocked and transported to us in the form of electrical energy to drive our technology. Now, these sources or resources of energy, they split into two groups. And there are those that are non-renewable and there are those that are renewable. We'll deal with the renewable ones another time. The non-renewable ones are coal, oil, gas and nuclear. And we'll talk about each one in turn. I love geology. Now, geology is the scientific study of rocks and what they can tell us. Now, all of these rock samples here have been collected from across the United Kingdom, mainly from mountainous regions, and they give us a little window into the past. Now, you see, things have not always been as they are now. That in the past, mankind did not exist yet, and there were other things, such as the dinosaurs, and before that, the origins of life itself. Now, these rocks tell us about those times. If we were to study where these rocks were in the geology, in the order of which the geology has been laid down, then we'd be able to look at what the conditions were like at the time when these rocks formed. And indeed, all of these rocks talk about and tell us with scientific evidence about what things were like in the past. Now, some of these rocks are much older than others. Some of these rocks actually are very, very old indeed. And to give an example, I want to take us out into the corridor. So here we are in the physics corridor. Now, I want you to imagine that this corridor represents the entire history of the Earth. At this end, the present day, and right at the other end, the formation of the Earth itself. Now, rocks have been laid down for the entire history of the Earth. And those rocks that I just showed you in my rock samples actually are representatives from all of those years gone by. And I have just here a rock that was formed only about 15 years ago. This rock was taken from the newly formed rock that had spewed out of a volcano in La Palma in the Canary Islands. And so this is a rock that is brand new. In contrast, I think we want to go back to the beginning of time. So as we start to go back in time, what we find is that we are going past about 1 billion years there, about 2 billion years here, about 3 billion years here, right to the very beginning of the whole Earth. And this other end of the corridor represents the beginning of the journey of Earth. Earth formed about 4.5 billion years ago. It did not look like this. The countries that you see drawn on a map are completely artificial, man-made. But the landforms, the continents, the oceans, are all things that have appeared at some stage in the history of the Earth. And now we're quite lucky because I have, just here, at about 4 billion years, one of the oldest rocks in the entire world. So what we see here is a sample of 4 billion year old anorthosite. This I had to sail to a remote island off the coast of Scotland to get a sample of this. This is older than life on Earth. That when this rock was laid down, the Earth was a volcanic, barren place. This predates the oceans. When the Earth was still warm and there were volcanoes everywhere, immediately after the impacts that caused the moon to appear. That is how old this rock is, and that is right back here at the beginning of time from our point of view. Now there are some rocks that come from this era, but most of them have been recycled by the processes of erosion on the Earth. There's a rock cycle where rocks are ground down into sand and then they form new sedimentary rocks yet again, and so the rocks from the oldest points in time, most of which have been lost to us now. It's in special places that we see that those rocks remain. Now if we go back forward past 3 billion years ago and then to about here, this is about the point where life first evolved. Life first evolved on Earth when the oceans had formed. Now the origin of the water in the oceans is still up for debate. An awful lot of that water came out of volcanoes, a mixture of hydrogen and oxygen. But some of it certainly arrived on Earth in the form of comets from space hitting in vast number. Now that water provided, with the energy from the sun, an amazing opportunity for chemistry to get very complex and self-replicating, what you and I would call life. But this is not we're not interested in the details of that for this video. We're interested in what life then did. You see, for a long time it stayed very, very simple. Single-celled organisms, kind of like the bacteria and viruses that make us poorly in today's day and age. But slowly, systems found that they could survive better if they were slightly more complex. And so life evolved. And as life carried on, we get to this time that's about 1 billion years ago, and that is where we see sort of multicellular things starting to exist, the things that are made of more than one cell, and cell specialization occurs. Now go further. Life comes out of the seas and starts to colonize the land, first with plant life and then animals thereafter. Now what I want to get to is this point in time that is about, 500 million years ago, so 500 million years. This is the point where the mountains of Snowdonia, including Snowdon itself, were formed and laid down as seabed. Now go just a little bit into the more recent times and we get to the Scottish Highlands. You see, this here is rock taken from the very top of Ben Nevis, and this was formed at about 300 million years ago. This predates the dinosaurs, but not by a lot. This speaks of a time when Earth was full of forest and plant life, and animal life was more simplistic, more like the insect and arachnid life that we see today. And this was the time of 300 million years ago, when the coal formed. And we'll talk more about this in a minute. But I'm going to put it down because I want to go forward in time to a mere 150 million years ago, the time of the dinosaurs. Because I want to show you this, which formed under the ocean at that time. This is oil. And this formed from all of the life that lived in the oceans at that time. But what you'll notice is, on the grand scheme of things, we are back almost in the modern day. That 150 million years ago is just a mere blink when we consider the full age of planet Earth. So back 300 million years ago, the world was full of plant life. Many very large trees of the kind like the monkey puzzle tree grew all over the world. And just as now, when those trees died, the wood fell to the forest floor. And falling to the forest floor, like all dead plants, eventually it turns into soil. And that soil gets compressed into further layers of soil, just as the clay does today. And then on top of that, what eventually happened was that layers of rock started to form through sedimentation being placed down over the top. As the world changed, what once was dry land became sea, and what was once sea became dry land, and what basically happened was rock built up over the top of this soil layer. Now, trapped in the soil layer was all of the carbon that these plants had extracted from that carbon dioxide-rich volcanic atmosphere that we had back then. And that carbon got compressed down by the weight of rock acting above, and it formed this coal. It is almost pure carbon, and this will burn. And so this is an energy resource. It's a fuel that, like wood, will burn in the right conditions. So the process of getting energy from this non-renewable energy source, the coal, starts with extracting the coal from the ground. Now, it quite often is very deep beneath layers of rock, and quite often in a seam. As you can imagine, as it was all placed down at one particular time and then covered with rock, that what you could find is that there is a layer underneath the rocks where this coal is now trapped. In the past, you would have a coal mine, and you would basically send normally children and very small people down to dig it out and to load it into things to be brought to the surface. Very dangerous work for a number of different reasons. Cave-ins, explosions, people getting trapped, all of these sorts of issues. In today's day and age, the machine has taken over where individual people would have done these tasks. And so in places where coal mines are still operating, what you find is that it operates as an open cast mine. And this is where they take off that entire top layer of rock, and with a giant machine, they just scrape up all the coal that is underneath. Either way, most of these produce coal for the railway, and what will happen is a series of wagons will be laden with coal, and then this will be transported across the country to your power station. Now, coal-fired power stations all start out like this. You'll have a giant mountain of coal, and the coal can be huge, hundreds, thousands of tons of coal dug up out in the open air, ready for their time inside. What will happen is a conveyor belt will pick up the coal and take it through into the workings of the power station. The first thing is the coal will get pulverised. A series of hammers will act down on the coal, turning it into a kind of coal dust. And the coal dust with oxygen is squirted into this, the furnace. And this furnace is almost exactly the same as what you have in your boiler at home. It's a place where a fire is kept inside a tank of water. Now, this fire burns really hot, and the rate at which it burns can be controlled by the amount of air and the amount of coal dust that gets injected in. You can make it burn hotter, you can make it burn less hot. And what this of course does is it heats the water in this tank around it. That's called the boiler. And this heat energy goes from the fire into the water, raising the thermal energy of the water. And as water will do, when it gets hot, it starts to evaporate. And it starts to evaporate and boil furiously. The steam tries to expand, as the gas will do, and there is nowhere for it to get out. And so it will force itself through a narrow pipe. And this will cause a blast of fast-moving steam down this pipe, which, when it hits this turbine, which is a glorified propeller, it turns the turbine. Now, the turning of the turbine, the axle of the turbine, is connected to a generator. And a generator, as we'll do later, is a coil of wire inside a bunch of magnets, and the turning of one relative to the other creates electricity. Now, what happens to the electricity is it then goes into a transformer, a device which makes it ready to be sent across the country. The steam is then collected on the way out into one of those very large cooling towers that kind of looks like a concrete volcano. And this helps recycle and get back that water so they can put it back in the boiler again, so that they don't have to keep using new water, they can just recycle it. This process is how we have generated electricity for over 100 years. It's very, very effective at generating large amounts of electricity. It, as a resource though, comes with problems. Coal. For a very long time, it was considered to be a wonderful thing. You see, it replaced the burning of wood. The problem with wood is that it just takes so long to replace. If you cut down the trees surrounding the place where you need the wood, then the next day you have to go slightly further and further and further. And what happened in prehistoric times was nearly all of the forests were chopped down. Now we know that if we chop down forests without replacing them, eventually you will run out of forest. And that was really obvious early on. And when they found this, they thought they had made a major breakthrough. Under our feet was all of this combustible material, and there was loads of it, almost unlimited. And so the problems went away, but they only went away for a short amount of time. One of the issues with this is it's not actually unlimited. There's only as much of this down there as formed at the time. And when we have dug it all up and burnt it, like the trees, there's nothing we can do about it. We will be out. Now there is a case to say that some coal is so deep that we'll probably never ever dig it up. But that coal is not commercially viable. And what I mean by that is it would take more energy to raise it to the surface than we would get actually out of the coal in the first place. So there'd be no point, we would gain nothing. Coal still exists in vast quantities in certain places around the world. But some countries don't have any coal left whatsoever. The United Kingdom has some coal, but it is at a depth that makes it questionable whether or not it's commercially viable to dig it up. But this isn't the only reason why coal is a problem. It's not the fact that it's running out that causes so much trouble. One of the main reasons why this causes trouble is the fact that we're burning it. Now with wood, when we burn wood, we release the products of combustion, water vapour and carbon dioxide, and some soot as well. Now that carbon dioxide was formed from the plant material as it burned. The plant absorbed carbon dioxide when it was alive. And so what came out of burning the plant was what was absorbed by the plant whilst it was alive. And so burning plant life, trees, wood, actually doesn't produce any extra carbon dioxide. It is actually something that you could do indefinitely and it would be in balance. But this is different. For this is carbon not present in our current ecosystem. This is carbon from 300 million years ago. This is carbon that originally came out of volcanoes that then, thankfully, luckily, got locked away again back under the surface of the Earth. If we release this carbon into our atmosphere, there are going to be problems. What happens with carbon dioxide in the atmosphere is that carbon dioxide will absorb infrared radiation. Now our sunlight contains some infrared radiation, but when the sunlight hits the ground, most of the sunlight that is absorbed then is re-emitted back into space again as infrared radiation. Think of it like the Earth's body heat radiating back away into space. Otherwise, if the Earth continued to just absorb and absorb and absorb, it would melt. But it doesn't. It gives the energy back to space in the form of this infrared heat. And now what carbon dioxide does in our atmosphere is it absorbs infrared heat. And it makes the carbon dioxide molecules move with more thermal energy than they had before. In effect, the carbon dioxide portion of our entire atmosphere is getting warmer. The more carbon dioxide we add to our atmosphere, the warmer it gets. This is the greenhouse effect. And it has now been found to be causing climate change. Climate change is where our weather systems, the temperature of the Earth, has been measured to be increasing because of this. This is a scientific fact. Burning coal is damaging our planet to the point where we are changing systems that we little understand that would cause us great harm if we continue to do it. So coal has had its day, and most countries are now trying to move away from coal. In an average year, we do not in the United Kingdom burn any coal anymore. One of the things that is true is that if it's a particular severe winter, we do keep some power stations online ready to burn coal should the need be there. It's a good emergency option, but it should not be our primary energy resource for those reasons. One final thing, coal is really dirty. Just handling it makes my hands go black. In the past, coal used to be delivered to people's houses and used to burn it on the hearth, and coal smoke would come out of their chimneys, and it would create such terrible air pollution that places like London had certain days where you couldn't see the hand in front of your face. In the 1950s, these were called pea supers and were really damaging to people. Now, the buildings of those times completely got covered in coal dust. And so the buildings of 50 years ago, St Paul's Cathedral and Westminster Abbey, were jet black with coal dust. Now, by taking coal out of the equation and actually removing the soot in those instances where we do burn it, what we're able to do is we can now clean our buildings, and our cities look much healthier and much prettier and picturesque than they would do otherwise. Burning coal is dirty, it is damaging to the environment, but as an emergency, it is a good standby resource for those times when we need to unlock energy in a crisis. So here we have a dogfish, and we have a jellyfish just here, and we have an octopus. And the thing that these have in common is that they're all dead. And for a very large number of years, things have been dying in our oceans. And where do they go? Well, they just sink to the bottom and get covered over with sediment. Now, this was happening 150 million years ago when life in the oceans was particularly rich with creatures just like these. All three of these were present at that time. 150 million years ago, all of that carbon material kind of like turned into a slime that got buried underneath rocks that were not permeable, so the slime could not move through the rock, it was trapped. And trapped underneath the ground, all of this turned into this. This is pure slime from dead fish and octopuses, and of course creatures around at the time like ammonites and belemnites. In fact, yes, this is foul stuff. This is crude oil. And we find crude oil basically underneath the rocks of the seabed. Even today, where the sea is now, is where the sea pretty much was 150 million years ago. So just out at sea, we can find that it is shallow enough that all of that material is extractable, that it is just underneath the surface, and we can extract this out, and we can use this as an energy resource. So oil can be found in a layer underneath some sedimentary rock, normally out at sea. And it's trapped there. And you have to understand that this is carbon from 150 million years ago. At no point has our present ecosystem contributed to this carbon. This is carbon from the past. Now you can see that an oil rig may sit on very long legs in those shallow seas and send a drilling head down through the limestone into the oil underneath. Then it is pumped up, loaded on board an oil tanker and brought to shore. In some places, where it used to be sea has now become dry land. The Arabian Peninsula, for example, recent geological movement has shifted all of what used to be a nice warm tropical sea to be now dry land and desert. And so in those sorts of places you can have an oil well on dry land, but you're still tapping down to the same oil as everywhere else. And this then has to be transported away. As soon as it reaches the land, you might find that the oil tanker docks at a refinery that is next to the ocean so that you don't have to transport it. But where you do have to transport it is if your refinery is inland, or maybe you are a landlocked country. In that case, you would probably find that on a train you would have your crude oil taken to the refinery. There it would be stored in very large containers before undergoing a process known as fractional distillation. Fractional distillation involves the warming of the oil. And what happens is the mixture of molecules that form crude oil start to evaporate one by one, starting with those that are lightest. And those lightest fractions are taken away for things like aviation fuel. And with heavier and heavier and larger molecules being used for things like the forming of petrol for our cars, diesel for our lorries, and also oil to burn in power stations. Now, there are not very many oil burning power stations left in the world, and this is because of the scarcity of oil, which I'll talk about. But when those power stations did exist, they operated in exactly the same fashion as a coal power station. Of course, it's also worth remembering that one of the byproducts of this is long chain hydrocarbons that we can use in the production of plastic. So out of this one mixture from 150 million years ago, we have aeroplanes flying, we have cars driving, we have power stations running, and plastics that are now used in nearly every industry. So what is the bad thing about all of this? First of all, there can be accidents when you're digging it out of the ground. An oil spill, either from an oil tanker as it's transported to the land or at the oil rig itself, can have disastrous consequences for wildlife. The Piper Alpha disaster in the North Sea and the Deepwater Horizon disaster in the Gulf of Mexico, both instances where the well broke and oil was released into the sea in great quantities. Now, to the fish and to the animals that live on the sea floor, it's not so much of a problem because oil floats. It is a different kind of liquid to water, and the two are not mixable. And it means that oil will stay basically the interface, the surface. But that is a problem to any creatures that must go from the air to the sea, or back and forward. So all of your mammals that live in the sea, your cetaceans, your whales, your seals, they have to go through the layer of oil to be able to breathe. The same too for your reptiles that live in your sea, your turtles, your crocodiles. But of course, there are the seabirds that hunt the fish that are in the sea. They have to go through the oil as well. An oil spill at sea is absolutely disastrous. And the chemicals used to disperse oil, which include things like detergents, they endanger wildlife in other ways. So the best thing to do is just to avoid releasing this into the natural environment. But then another issue is, of course, the scarcity. All of the oil that is easily obtainable has been obtained, and it is gone. The only oil left is those where it is more challenging to extract, either because it is really deep, it is under the sea where it is too deep for a oil rig to stand, and then you have to have a floating oil rig which has to maintain its position whilst it drills on a very, very long cord down to the bottom. Can't imagine how that might go wrong. But then there are other issues as well, that the places in the world where this oil might not be particularly very stable places. And this, as well as fueling our cars, might also be fueling wars, people fighting over some very scarce but very valuable resources. Is that something that we want to fund here in the Western world with our money? No, thank you. Other issues is that the technology that we've gained from understanding and cracking oil is also producing carbon dioxide when it is burnt. So from car engines, from lorries, from trains, from aviation, we are producing a huge amount of carbon dioxide. and this is entering our atmosphere and contributing to global warming and climate change. As well as that, oil, there is another problem, in that the materials that we can make from oil include this: plastic. Now don't get me wrong, plastic is a wonderful material. It is hard-wearing, it is formable in any shape or size you want. Think about how clean things like medicine can be because of just how resistant to bacteria a plastic surface can be. Think about how we can make the food of the earth go, stay in date for longer. The perishable items don't perish nearly so quickly. We can keep the earth so productive that the people on the earth do not starve because of this. But this also does not break down. This is a totally man-made material, and nature has not encountered it before. There is no organism on Earth that knows how to break this down and break those molecules. And so plastic will endure in our environment for an unknown but very long length of time. And that is very bad, because in the last 50 years, trillions of tons of plastic have ended up in our ground and in our oceans. Now, when fishermen catch fish, they catch almost as many pieces of plastic from the ocean. A quick walk along the beach shows just how much plastic is now floating in the sea. This has been a wonderful thing, but we have used it irresponsibly. And so this is a major downside of what we've found from oil. Now there is one further fuel that we can extract from fossil life from a long time ago. It is the third one of the fossil fuels, and it can be extracted from both places where coal is found and where oil is found. It is, of course, natural gas. Here I have some natural gas. You might recognise this as the gas that's used in science labs. It's also the gas that's used to power your boiler at home. And it burns very cleanly, there is no smoke, and it can be used to heat up water, whether it be on your stove. If you have a gas-powered oven, you may recognise the familiar burning of this. So where does it come from? So there are three main sources of natural gas. What you could find is that here, down in the oil well, if the curvature of the land is such that you have basically here like a dome, an underground cavity, then what you would find is oil would form at the bottom of that cavity. But natural gas, being made of molecules that are much smaller, would probably tend to be gas at these kind of temperatures and pressures. And so what you would find is that in this little pocket here, like an air pocket, you would have natural gas accumulated under the ground. Another thing that you might find is when you tap into the oil under the sea and you start sucking it out, it lowers the pressure inside the oil well. Lowering the pressure enables the gas to come back out of solution. And so you actually end up having gas produced by the oil in front of your eyes. Now, a more recent method of extracting gas, if there is none available, is by fracking. Now this is looking for another source of gas known as shale gas. It's the same gas, but its position is different. The gas can be given off when all kinds of biological material decays. And it doesn't have to be down in an oil well. What they've found in places where there are deposits of gravel and other small sedimentary particles is that in amongst it are tiny bubbles of natural gas trapped and can't get out. And so some bright spark came up with the idea of flushing it. If you put high pressure water through those sediments, what will happen is it'll knock all the gas bubbles out and you can collect that. The controversy caused by fracking is, first of all, the industrialisation of natural places, but there's also some people that think that it could cause earthquakes, that it could cause places where you have water subsiding and forming sinkholes. But these are the same kind of issues that mining in general create. So there's nothing necessarily new about this technology. The natural gas can then be piped and stored in giant gasometers, huge, great big round tanks. You quite often see them near train stations because it's normally trains that carry under high pressure the natural gas. And this could be fed straight into a power station, firing those boilers, or it could be delivered via a gas pipe to your house, to your laboratory, to your factory, wherever. The final source of natural gas is actually from the fractional distillation column of oil, one of the products when you split crude oil into all of its various different mixture compounds, is that natural gas is a major one that is given off. Now, natural gas burns very cleanly, and we can extract it from a number of different sources. Surely this is the perfect non-renewable resource. So what could be the problem with gas? Well, it's running out. It is a limited resource. We only find it in places where we have to dig through the Earth's crust to obtain it. That the issues with extracting oil from the ground are also the same issues of taking gas from the ground. Fracking as well adds additional environmental impacts at that first level. Now, the burning of natural gas can cause problems as well. If gas leaks into your house and there is a sudden combustion, then it can explode your whole house. A gas leak is very serious, but if everything is very carefully controlled, it is not dangerous. It's only dangerous when things go wrong. And hopefully with legislation and safety protocols, things go wrong very, very rarely. However, as with the other two fossil fuels, the burning of natural gas produces, you got it, carbon dioxide, which is one of the main contributors to the greenhouse effect, global warming and climate change. The fact that we can't use it forever and that the burning of this fuel causes us problems is a reason why we have to start looking at alternatives. So we have these fossil fuels, and they include oil, coal, and natural gas. That is the three fossil fuels. There are no more than that. That is all of them. But these are not the only non-renewable energy resources. There is a different type that is not a fossil fuel. And so if I was putting non-renewable resources in one family, there would be the fossil fuels, and then there would be this second family, which would include nuclear resources. So let's talk about nuclear. I am here in a secret location, getting into which required using a key to get to this place. And inside this secret location we have a security cage. Now what I'm going to do is I'm going to just lock. There we go. Take that off. Now we're in to a place that is very hazardous indeed. Here we have an old-fashioned goldsmith safe. The sort of safe that you would find in an old-fashioned bank. Using a different key, I'm going to open the safe. You'll notice that the trefoil of danger is on the safe. I'm going to open the safe, if I can do it. Hopefully there is the safe opened. And what we have inside radioactive samples. And so here that you can see radioactive material stored inside a hardened safe. The metal casing of the safe prevents the radioactivity from getting out into the world. Now what we can see at the very bottom of the safe, and I shall handle it only very quickly because I don't wish to expose myself to very much radiation, is a box of rocks. These rocks are naturally radioactive. They are all ores of the material uranium, and uranium is used inside a nuclear power station as a non-renewable energy resource. Let's have a conversation about it. So I have here some of that uranium ore, and in here is an unstable element. An unstable element that can be processed into something known as fuel grade uranium. And here, this is quite heavy, is a bar of fuel grade uranium. Now you mustn't touch this. This here is giving out a small amount of radiation all the time. But the thing about this that makes it useful is that what we can do with this is that we can trigger a nuclear fission reaction to occur inside the uranium atoms, in the nucleuses of those atoms in this rod, by placing it next to another rod that is doing the same thing. And so here you can see I have two sets of rods. They're all made out of uranium. This is called a fuel bundle, and this is also a fuel bundle. And what they do, if a single particle sets it off, a particle called a neutron, then it will cause multiple reactions to happen that go on to cause more nuclear reactions. But they're only successful if something can be placed between the two rods that slows those released neutrons down so that they can be successfully absorbed by the fuel rods on the other side, and then the reaction can carry on. So here I put a special material called a moderator, and what I'm going to do, I'm just going to wind the moderator up. At the moment no reactions can take place because they are just producing neutrons that are too fast. As I slide my fuel bundles into the moderator, then what will start to happen is nuclear fission reactions can occur triggered by the other rod. So basically what happens is a single stray neutron causes a uranium atom to break down in this fuel rod, and that fires out a spray of fast moving neutrons that are then slowed down in this moderator liquid to enable them to go on and have another reaction on the other fuel rod. And this carries on and carries on and carries on, generating huge amounts of heat. Let me turn the light off and you'll see. Here we go. So you can see that here the Cherenkov radiation, as the neutrons are slowing down and they're travelling faster than basically the speed of light in this material, that nice warm glow of a nuclear reaction. And now in a nuclear reactor this has to happen in a totally sealed environment for it to be safe. Here we just have it in the classroom. But what you can see is that this, through the process of nuclear fission, can produce a whole load of thermal energy. Now the fuel, the uranium ore, does not at any point in this process bring carbon from an ancient ecosystem with it. And so this, even though it is non-renewable, actually is not going to produce any of that pesky carbon dioxide that has caused so much of a problem with the other resources. But it does cause some problems, and we'll talk about them now. So how does it work? Well, you have the uranium fuel rods inside this vessel that is sealed off from the outside world. This is the nuclear reactor. And these fuel rods are encased within a special substance known as the moderator. Now what happens is uranium breaks down because a neutron has hit it. and in breaking down, it produces a spray of fast-moving neutrons. Now, of course, we will go into more detail on this in the radioactivity topic, so this is just a beginner's eye view. The neutrons go through this moderator and they lose some of their kinetic energy. The neutrons go on to cause further reactions in the other fuel rods, and so reactions occur when a neutron successfully goes through the moderator, slows down, and then is absorbed by another fuel rod. And this goes on and on and on and on for as long as you like. And now what happens, every time this moderator absorbs some of the kinetic energy of the neutron, it makes the moderator slightly warmer, because there has been an energy transfer from the kinetic energy of the particle into the thermal energy of the moderator. And so they keep the moderator cool with coolant water that they surround the whole tank with. Now notice that the coolant water never comes into contact with the fuel rods, and so long as no contamination can occur, it's perfectly safe. The coolant water starts to get hot, and in doing so it starts to boil, producing steam which hits a turbine, turning the inner parts of a generator, generating electricity as before. But notice there is no chimney in this whole process. There's no carbon dioxide given off, and the fuel itself is readily abundant on the Earth. There is a huge amount of uranium left for us to use. Furthermore, rather than a giant mountain of it, only a very small amount is required to power one of these reactions. And there are safety features. Not only is this completely an enclosed system, but this water is possibly recycled. That if the reaction starts to go too fast, you slide in barriers to stop the neutrons from successfully going from one fuel rod to another. These are called control rods. Nothing to fear, it's all good. So nuclear, it's amazing because it gives us a huge amount of energy from a very small amount of fuel, and it doesn't add significantly to global warming. What's not to love? Well, the issues with nuclear became apparent really early on, in that once the uranium has fired neutrons into another uranium atom, that uranium atom breaks into pieces. Those pieces are left in our environment. We call them nuclear waste, and nuclear waste is really bad to human health. Nuclear waste is actually really, really toxic to our cells. That radiation can give us cancer and can also cause mutation and sterilization. And worse is that not only could there be large accidents which result in the countryside and the ecosystems around being contaminated by radiation, that the technology involved in designing this is also the technology involved in designing this. And you wouldn't want some crazy person like developing nuclear weapons and pretending that they were trying to develop nuclear power. And so nuclear energy has some significant issues. This radioactive waste is going to continue to be radioactive for tens of thousands of years, posing as a real threat to humanity for all that time. Very big disasters like Chernobyl, Fukushima, these showed us that for all of the safety systems we put in place, the consequences of it going wrong were so high that we have to ask the question, was it worth risking it for the energy that we got out of it? Now this concludes our look at non-renewable energies: oil, gas, coal and nuclear. Now what you probably realise is that though we can get energy from all of these resources, each comes with its unique problems. In the next video, we'll look at renewable energy sources, and we will try to measure that with the same eye of fairness that we've cast over these resources.